Okay, let's start a new topic, error analysis. So what do we mean by error? Look, if we are measuring any physical quantity, there is chance to get some uncertainty in result. So that uncertainty we call error in measurement. So this is called error. Now let's introduce two terms. One is accuracy and another is precision. Accuracy and precision. So what do we mean by accuracy and what do we mean by precision? This is term for the measured value, how close the measured value is to the reported value or to value obtained theoretically. And this term is for up to what extent the resolution of the instrument is the instrument which we are using to measure some physical quantity, and the extent of resolution we call that actually the smallest amount that can be measured we call that least count. We are going to discuss these things later. But if we are using greater resolution scales, greater resolution instruments, we are measuring the values more precise. Let's take an example so that it will be obvious. Let's say there is a line segment AB and its reported length is 4.2 centimeter. Now, if we are measuring this line segment with a scale having 1 centimeter marks, means this scale has least count of 1 centimeter. It can measure up to smallest distance up to 1 centimeter. So let's say if we are getting the value 4, actually it will be 4 only, not point. So 4 centimeters. Now we are measuring the same line segment, means the length of this same line segment with another scale. Let's say this is second scale, and this scale can measure up to 0.1 centimeter length. So least count is 0.1 centimeter for this scale, and we are getting the measured value 3.8 centimeter. So now we have two different scales, two different readings for these two scales, and in one case we are getting a closer value to the result. So this value is more accurate. This 4 centimeter is more accurate. What we can say, the accuracy in measurement is more in the case of first scale. While measurement, we are using this 0.1 centimeter scale and it has greater resolution compared to this scale first. So precision is more in second case and accuracy is more in the first case. So this way, accuracy is how close the measured value is to the reported or to the theoretically obtained value, and precision is up to what extent of resolution the instrument is being used. Means the instrument which we are using, if it has greater resolution, means we can measure a physical quantity with great precision. So more precision comes from higher resolution instruments. Okay, now moving to the next point, and this is classification of errors. Once we get that, okay, if we are measuring something, we are getting some errors, means some uncertainty in measurement, we can classify these errors based on their origin. And here we have two broad categories. One is systematic error and another is random error. So let's start with systematic errors. Systematic errors, we can call it, it comes from faulty instruments or imperfection in experimental techniques, or maybe some personal error like carelessness, you can say. Let's take some examples of these things, then it will be more clear to you. So let's take first one, instrumental error. So in case of instruments, let's say you are measuring electric current with a milliammeter, and if it is not connected to any circuit or current is zero in the circuit, and still its needle is not coinciding with zero reading, it is coinciding with some other reading. So this is a kind of an example of instrumental error, and we call this error as zero error actually. So this way, there may be faulty instrument, and because of those instruments, we can get some errors. These errors are classified under systematic errors, and we call it these errors instrumental errors also. There may be other instrumental errors like poorly calibrated magnetic compass. If there is, in case we are using some broken, let's say we are using a ruler and it has been broken from this end, and its scale is starting from 1 centimeter instead of 0. This is another type of zero error. So in this way, in case of screw gauge or micrometer, there may be backlash error where measurements will be different if you are measuring the values by rotating counterclockwise, and if you are measuring the value by rotating the micrometer in counterclockwise and clockwise direction. This way, you may get different values. That is from backlash error. So instrumental errors can be eliminated by using, up to some extent, this can be eliminated by using proper instruments. And imperfection in experimental techniques may be also there. So that can be mitigated by improving our experimental techniques, by studying thoroughly about experiment. And of course, there may be personal errors. So personal errors, basically, this can come from carelessness. So there may be personal errors which can come from carelessness, like parallax error. Let's say you are measuring, uh, let's say you are measuring amount of fluid with the help of measuring cylinder, and here you are getting markings. So if the fluid is up to this level and you are not watching it horizontally from here, you are watching from here, let's say. So this level of the fluid will coincide with this lower marking, which won't give you the accurate result. You may be reading the amount of this fluid lower than actually it is. So this way, errors can occur, and these errors we call personal error. And these errors can be eliminated, or at least up to some extent, these errors can be eliminated by using proper techniques, by being cautious and sincere while doing experiments. Okay, after systematic errors, let's discuss about random errors. And these errors come from unpredictable fluctuations in experimental conditions. Fluctuations in experimental conditions. Okay. So these errors come from unpredictable fluctuations in experimental conditions. Like if you are performing an experiment in laboratory, there is chance that temperature, atmospheric pressure, and of course humidity, these things may change. So, and of course, in case of you are performing an experiment with electric circuits, so there is chance to get fluctuations in voltage as well as current. So these errors are there, and we categorize them in random errors. Even if you are controlling the experimental condition up to certain extent, still if you are measuring the values, suppose you are, let's take an example, then it will be more obvious. Let's say you are using a stopwatch and you are measuring time period of oscillation of a simple pendulum, let's say. So in first case, suppose you have measured a value 2.52 second, but it is not necessary that in second case you will get the same value. Maybe in second case you are getting something 2.40 second. So even if you have controlled up to certain extent the experimental conditions, still at different instances you will get different results, at least slightly varying results while doing measurement. So this is 2.58 second, and one more reading, let's take 2.50 second. So you have measured the time period of this simple pendulum at 5 different instances, and you are getting these values. So of course there are uncertainties, and these uncertainties are very random. So these uncertainties are not coming from any kind of instrumental error or imperfection in experimental techniques or personal error. These are just coming randomly. So these errors can be estimated actually. We can use some calculation techniques, and then we can minimize the effects of these errors. Or of course, in calculation, we will consider these errors, but in a way that we will get a proper value. How do we perform that calculation? Although there are several different ways, but let's take a simple example here. So we what we do actually, we report the value along with the possible error coming in that value. So how do we do? Let's take mean of these values. So T mean. This will be sum of all these values divided by number of readings taken. And if you add these things and calculate, I think it should be 2.52 seconds. This is T mean. Now, this is mean value. We have the term absolute error. So, if we are taking difference of mean value and a particular reading, then we will get this absolute error for that reading. So in this way, let's take example from there. The mean reading is 2.52 second and T1 is 2.52 second. So in first case, it is 0. Now in second case, the absolute error for the second reading will be, let's take example from here. This will be 2.52 minus 2.40, and that will be 0.12 second. And that will be, in this way, we can get absolute errors for other measured values. And let's say delta T3, it will come. If you calculate, I have calculated here already these things. So delta T4 will be 0.06 second, and delta T5 will be 0.02 second. Okay. So after obtaining absolute errors for these measurements, we can get mean value of absolute errors, and that is nothing but we have to add all these absolute errors, and then we have to divide by the number of terms. So this will come, you can add all these things and divide it by 5, and then it will come 0.06 seconds. So we can report the value here, P mean plus minus the mean value of absolute error. This will be the time period of this pendulum. So T mean is 2.52 second, and we have error. Let's not write second here, and we have the mean value of absolute errors, that will be 0.06 second. This is time period for this pendulum. We can report it. Okay. Okay. Uh, After this absolute error, we have relative error also. So what do we mean by relative error? It is nothing but, let me clear it and then, okay. So let's take measurement, time period equals to 2.40 second, and the mean value or reported value or theoretically obtained value, let's say, is 2.52 second. So absolute error will be delta T, which is T mean minus T, 0.12 second. And now there is a relative error also, and relative error we can write it as delta T by T, and this will be 0.12 second divided by 2.40 second. And of course, if we want to get percentage error, the only thing we need to do here, Already we have fraction here. We have to multiply it by 100 and then we will get percentage error. So we can calculate this thing. So this way we have a particular measured value, we have reported value or mean value or theoretically obtained value. And if we are taking the difference, this difference, absolute value of this difference, we call it absolute error, and absolute error divided by the measured value, this is called relative error. And this relative error, as it is already in terms of fraction, we can multiply this value to 100 and then we can get the percentage error. Okay. So after classifying the errors and studying systematic error and random error and taking an example how random errors can be estimated, let's move to next point, and that is least count error. So no matter how systematic you are performing your experiment or how controlled the experimental conditions are, there is always least count error because it comes from the resolution of instrument. So how it comes from actually? Let's take an example, then it will be more clear. You are measuring the length of this line segment. So you have used a scale having resolution of 0.1 centimeter. Least count of scale is 0.1 centimeter. What does it mean? That the scale has markings at intervals of 0.1 centimeter. So this is the smallest length this scale can measure. So least count of this scale is 0.1 centimeter. But what happens? Let's say you have measured the value 4.2 centimeter. Let's say you are measuring the exact value 4.2 centimeter. Still there is uncertainty because after, let me draw and then we can discuss. This is 4.1 and this is 4.2. So now take a closer look to this 4.2. If the line segment falls up to here, just coinciding with this 4.2, you can report the value that, okay, the line segment has length of 4.2 centimeter. But if it is slightly beyond the 4.2 and just, or maybe just before this 4.2, still you will report this value to be 4.2 centimeters. That's how the least count error comes into picture. So you look, it is closer to 4.2, so you can't report it 4.1 centimeter or 4.3 centimeter. So you have to report this all the length. Look, all these three line segments, you have to report the length as 4.2 centimeters. So whether it is lying here or exactly coinciding at 4.2 centimeter or here, you have to write this value as measured value 4.2 centimeters. So there is uncertainty at this terminal. Now, how much uncertainty is this? This uncertainty is nothing but its least count. So this uncertainty is equal to its least count. Now, how can we get the relative error in this scenario? So least count is 0.1 centimeter and the measured value is 4.2 centimeter. So we can write relative error in measurement, that is, let's say delta L by original L, 0.1 centimeter, which is least count divided by 4.2 centimeter. This is relative error, and if you want to get percentage error, this will be 0.1 by 4.2 into 100. So in this way, or you can report the values of the measurement taking the errors into consideration. Now coming to next point, propagation of errors. What happens actually? If you have measured two different values, let's say you have measured a quantity A and you have measured another quantity B, and the absolute error in these two quantities are delta A and delta B. Remember, in case of list count, the absolute error is list count error actually. As we have taken this example, here the absolute error is the list count of the instrument. Otherwise, we have taken another example where we were obtaining the absolute error by taking mean and the difference of particular measured value. That is the absolute error for that particular measured value. So this way we can get absolute error actually. So coming back to the discussion, A and absolute error in this measurement is delta A, and B another measured value, and absolute error in this measurement is delta B. So how do we report these values? We report A plus minus delta A, and for B we report B plus minus delta B. So this way we can report these values. And if we are adding or subtracting, let's say there is another quantity Z equals to A plus B. So we can write this thing Z along with absolute error in delta Z, in Z, that is delta Z. We can write it as A plus B, and then we have plus minus delta A plus delta B. So we can see here that delta Z is, this value is Z, this value is now delta Z. So we can see here delta Z is nothing but delta A plus delta B, and this is the propagated error. So if we have two different measured values, and this can be generalized for n values also. So if we have two different measured values, and absolute errors are delta A and delta B, let's say in these two values A and B. So if we are adding or subtracting, we will get net error in Z, that will be delta Z, and it can be obtained from these two absolute errors by just summing them. Now let's take second case, when we have measured these two values and we have multiplied these two values to get another value, how error will be propagated. So let's say delta Z is absolute error in Z, and this absolute error we have to decide. So A can be written as, along with its error estimation, A plus minus delta A multiplied with B plus minus delta B, and then we can write AB plus A delta B plus delta A into B plus delta A into delta B. Okay, now you can think that, okay, here is plus minus sign, so here it should be okay, we can write it. And of course, here we can write it plus minus sign, of course here also. But this thing we can ignore, because look, delta B or delta A, these are already very small quantities comparing this value, comparing A and B. So we can eliminate or we can neglect this quantity, because this will be practically negligible comparing these quantities. So we have here plus minus delta Z equals to AB plus minus A delta B plus minus delta A into B. And then we can divide all these things by Z. Here we are dividing by Z, and Z is A into B. So here we are, because every each and every term is A and B here, so we are dividing it by AB, which is nothing but Z. So here we will get 1 plus minus delta Z, and here we will get 1 plus minus this A, and A will be cancelled out in this first term. Here we will get delta B by B plus minus. Here delta A will be there, but B and B will be cancelled out, then delta A by A. And look, both LHS and RHS have 1, so this 1 will be eliminated from here. And then delta Z plus minus delta Z will be plus minus this and plus minus this. So delta Z will be nothing but divided by Z will be delta B by B plus delta A by A. So what is happening here? If we got value by multiplying these two things, the propagation of error will be, relative error in Z will be sum of relative errors in these two values, what we got here. Okay, the same argument we can carry forward to get the propagation of errors in terms of power. So if we want to get propagation of errors A square, the only thing we need to do, replace this B by A, and then we will get here delta A by A, and this will be 2 times of delta A by A. So here relative error will be propagated as twice of delta A by A. Okay. Now, if we want to get A square into B, Then after this, there will be another delta b by b. Okay. And the same argument we can carry forward for C. Let's say z equals to a square b divided by c cube. So there will be delta c by c, thrice of delta c by c. And look, errors will be accumulated only. Errors are always accumulative in nature. So don't think that this c is in division. So this can just eliminate some errors from the measurement. No, if there is error in this term c, it will be added in the final result. So in this way, if there are powers, let's say instead of here another d that has power 1 by 2 or a square root of d. So you can write here 1 by 2 delta d by d. In this way, you can continue the argument. Okay, at the end, let's take a numerical example. Let's take, we have measured length and breadth of a rectangle. Length is 2.5 centimeter and breadth is 0.5 centimeter, let's say. And we have used a scale having list count 0.1 centimeter. So absolute error in the length will be 0.1 centimeter, and we have used the same scale for breadth. So absolute error in breadth will be 0.1 centimeter. Now relative error, so delta L by L will be 0.1 centimeter divided by 2.5 centimeter, and relative error in breadth will be delta B by B, which will be 0.1 centimeter divided by 0.5 centimeter. Okay. Next, if we want to get perimeter of this rectangle, so perimeter is twice length plus breadth. So if we want to get perimeter, there will be propagation of errors coming from these two measurements. And as we have studied earlier here, in terms of summation or subtraction, here just absolute errors will propagate. So we can write in this case, the absolute error in the measured value of perimeter will be 0.1 centimeter plus 0.1 centimeter, that is 0.2 centimeter. And we can report this value perimeter to be twice of L plus B. This will be 2.5 plus 0.5, that will be 3 centimeter, twice 6 centimeters. So 6.0 plus minus 0.2 centimeter. This way we can report the value for perimeter. Now coming to area of this rectangle. So if you want to get area, what we need to do? We need to multiply this L into B. And here we are using multiplication of two terms. So area A equals to L into B. And we know delta A by A is delta L by L plus delta B by B. From our previous argument here, if this is L, this is B. So the relative error in area will be the relative error in length and the relative error in breadth here. So these two things we can add to get relative error in this thing. So this way you can report area equals to whatever be the L into B, that will be 2.5 into 0.5, and I think it will be 1.25. So that value and plus minus, this is relative. So if you want this delta A, you have to calculate this thing and then you have to multiply with A. Then you will get this thing. So here you have to write delta L by L plus delta B by B into A. This will be the reported value for area here. So the only thing you need to do is to put L and B values here everywhere to get the numerical figure. Or there is another thing. We can write all these things in terms of percentage error. For example, if we want A equals to L into B and delta L by L is 0.1 centimeter divided by 2.5 centimeter, ultimately centimeter will be cancelled out. So we can write percentage error. So this will be, I think, 4%. Yes, 4%. And percentage error in breadth will be delta V by 0.1, 0.5 into 100, that will be 20%. And what happens in case of area? This percentage error will be accumulated. So if we want percentage error in area, this will be 24%. So area, we can write L into B plus minus 24% of this value. And this we can get 2.5 into 0.5, that will be 1.25 plus minus 24% of this value. And then we can write it A equals to 1.25 plus minus, what will be the 24% of this value? And this will be very less. You can calculate by yourself and write it here. Okay, not one thing here. Here we have measured, here we have reported the value. After measurement, we have calculated this area and we have reported that it is 1.25 plus minus. So this is not the exact way to report actually, because we have to take care of number of significant figures, and the least significant figures in our measurement will be reflected in the final result. We are going to discuss about significant figures, and then we will know how to report the final value in accordance of the significant figures. So that will be very important discussion, and you should not miss the next video actually.